We shall get ahead with the main focus of the course, which is statistical mechanics. And once again we ask this question that if thermodynamics has been successful in giving us the parameters, the basic parameters of the system such as pressure, volume, temperature and maybe the density of particles, then why do we need statistical mechanics? Statistical mechanics is needed in order to understand the internal structure of the system, that is how different particles are arranged in different available energy levels, so as to give us the pressure that we get or the volume that we get or the temperature that we get. Okay. So, it gives a total description of the system, and thermodynamics actually deals with very few parameters, and that is why the study is simple, but the scopes are limited, whereas statistical mechanics supplements what is not answered by the thermodynamic either the laws or the variables in totality there, the explanation is not completely given by thermodynamics. So, we will start with statistical analysis, and what we mean by statistical analysis is that that we will learn how to deal with statistical systems, that is a large number of systems. In fact, a priori I should tell you that the results of statistical mechanics is going to be flawed if the number of systems or the number of entities or the number of data points are small. In fact, we need large number of data points, and in order for to make a statistical interpretation, and the statistical analysis will mainly do it on two problems. They are shown here. There is a random walk problem that you see here, and there is a coin tossing problem, and the random walker, assumably a drunken man, he starts from a landmark, say on the road, and he places a step on the right and on the left with distinct probabilities, and each step he takes on the right or on the left, they are statistically independent of each other. And the only constraint that we are making is that he takes equal the step sizes are of equal length L, and so the direction of each step taken is randomly either to the right or to the left with probabilities p and q respectively. Okay. So, he takes a step to the right with a probability p, and he takes a step to the left with a probability q. We ask this question, what is the probability that the position of the man after n steps is x equal to ml. Okay. Where m is a number, and it denotes here, it denotes the difference between the right and the left steps taken by the man. And the coin tossing problem should be more familiar to anyone who has done probability. So, it is a tossing of a coin yields either head or tail with equal probability, which means with half probability. So, we ask this question, what is the RMS and the average value of or average values of h minus t, that is head minus tail, obtained in this experiment of tossing coins after n such tossings. And interestingly, we will see that these two problems have common outcomes. So, there is a schematic of a drunken man, as you say that he is taking steps to the left or to the right on this landscape. There is a lamp post just to sort of tell his with respect to what we should measure. And so, we ask this question, what is the nature of the path when the walker has taken n steps, and this at random to the right and to the left with probabilities for the right step is a probability is p, and for the left step the probability is q. The peculiarity of the paths is, this is a priori, let me state the results. A small portion of the path looks exactly identical to a bigger path. So, what I mean is that if you look at a small portion, say here, that is going to look at identical to something which is looked at a bigger scales. And this is a very interesting phenomena, and we will see that later, that close to phase transitions, we are familiar with a large number of phase transitions such as paramagnet to ferromagnet, water to ice, or water to vapor, and so on and so forth, superconductor to metal, say for example. And this phenomena, where the small portion looks identical to a much larger portion, is called as scale invariance. When they start looking same, it says that it is this called scale invariant. In fact, if you think of a paramagnet, then it looks different at all length scales, which means that in a certain region of a paramagnet there could be some more spins pointing up than pointing down, and if you go to another region or a bigger region, you will see that there are more down spins that as compared to up, and so on and so forth. But when the system undergoes a transition to a ferromagnetic phase, either as a function of the applied field or by reducing temperature, then these all the spins are pointing up. So, if you look at 5 spins, or you look at 5,000 spins, or 50,000 or 5 million, it really does not matter, they all look same. That is called a scale invariance, and this scale independent behavior, it gives a universal property, which is called as a universality to the system, which would be discussed when we talk about phase transitions. And these self similar or the scale invariant objects are also called as fractals because of the fractional dimensionality. We will not elaborate that, but let me show it via this animation. So, you see that this is zooming out, and you or rather zooming in, and you are seeing these kind of structures, they are appearing at all length scales. So, for the first half of the video, it will zoom in and will go closer and closer to this, and as you come closer, each of these structures that you see here, this mushrooming structure, they would look exactly the same. So, and it is not only for zooming in, it will happen for zooming out as well, which is just what we are going to see in a while. So, now it will zoom out, and it is probably self explanatory that it is going to look the same. So, now you see the same structure is appearing as you are zooming out, and these are same at all length scales in the of the problem. And these are called fractal structure or self similar structure, and there are many examples of fractals. You can have fractals at the seashore, you can have fractals, you can make fractals, a fractal structure which are called as Stokes curve, and so on. Okay. All right. So, all these are fine, these look nice and so on, and we understand what is meant by scale invariance. But what is the main question, physics question that we are asking in this regard? One of them can be said as this, that if we add n vectors of equal length, but in random directions, okay, and ask for the probability that the resultant vector after adding n of them has a certain magnitude and direction. So, this is the question that we ask. And what are the examples of such a physical phenomena? The magnetism is one such phenomena, where we talk about n particles, each one with magnetic moments m equal to plus half or minus half, which can either point in the up direction or the down direction. So, we ask the question, what is the net magnetic moment of the system, which is same as what we have asked earlier, that if you add them vectorially, where do you go and land as compared to your initial configuration. So, what is the net magnetic moment of the system? Diffusion, this is in the Drude's theory, that an particle, or here we are talking about a molecule, randomly moves after a collision. So, between two such collisions, they drift like free particles, and when they come and collide, and after collision they move in all possible randomly in all possible directions. So, the question is that how far is it likely to go after n such collisions, and that should be related to conductivity and so on. So, let me now do this random walk problem, and so once again to remind you that there is a drunken man or a drunkard who is taking randomly steps to from towards the right and towards the left with probabilities p and q respectively. Okay. So, he takes n steps, each statistically independent and of length L. So, each step size is L, and he takes n of them with probabilities. So, P denotes the probability to take a right step, and Q denotes the probability to take a left step. And they are independent of each other. Okay. And so, we ask this question that after n steps, what is the probability that the man is at a location given by x equal to ml. L is the, as I said, is a each step length, and m is an integer. And m essentially is a difference between the right steps taken minus or difference between the right and the left steps taken. Okay. So, n1 is the number of right steps taken after capital N steps, and n2 is the number of left steps taken. This automatically fixes capital N equal to n1 plus n2, and m, which is a difference between that, is n1 minus n2. Okay. Or it could be n2 minus n1, but just without any loss of generality, we are taking it to be n1 to be greater than n2, but it could be n1 could be also less than n2, in which case m would be negative. So, if we use this, then we can write down this m as 2 n1 minus n. Okay. So, this is one small observation is that if n is odd, m is odd, and if n is even, m is even. So, m, small m and capital N, they follow each other in terms of being even or being odd. All right. So, we know of this already. Now, as I said that the probability of taking a right step is statistically independent with that of taking a left step. So, probability of taking n1 left steps with probability of p and the probability of n2 right steps with probability q is given by p to the power n1 q to the power n2 and so on. Okay. So, suppose that he has taken 2 steps, then there is a possibility that, and since they are independent, so it is p into q, and if he has taken 2 steps towards right and 1 step towards left, it will be p to the power p square into q and so on. So, that is why for n1 left steps and n2 right steps, and because they are statistically independent, we can write the probability to be the multiplication of the 2. But there is more to it, because how we can arrange n1 and n2 so as to make it n. Okay. So, this is given by there are many possible ways. The distinct possible ways of taking n1 and n2 steps to make a total n is that is the distribution which is given by n factorial, n1 factorial, n2 factorial and so on. So, let me just for a moment consider capital N to be 3. So, if capital N to be 3, then n1, n2 and m this can be 3, 0. So, this will be like 3, this could be like 2, 1, this could be like 1, this could be 1, 2, minus 1 or 0, 3, minus 3 and so on. So, these are the different ways of arranging or rather finding n1 and n2 giving rise to a total capital N of 3. So, this is that probability. So, the probability of taking n steps the total probability rather of taking n1 steps to right and n2 steps to left is the probability, let us call it as P n n1 n2 is just a notation, you can use your own notation, is n factorial divided by n1 factorial into n2 factorial and p to the power n1 and q to the power n2. Okay. So, this is the probability that we the man had taken capital N steps with n1 randomly towards the right and n2 randomly towards the left with probabilities p and q, and this is called as a binomial distribution. All right. So, we know the formula for binomial distribution. So, we can write it as p plus q whole to the power n is equal to sum of n equal to 0 to n, and then we have a n factorial divided by n factorial small n factorial n minus capital N minus small n factorial p to the power n q to the power n minus n. Okay. So, this is the binomial distribution, you can easily check it for say a cube for example or to the power 4. So, you will get these coefficients, like for example, we know p plus q whole square equal to p square plus 2 p q plus q square, and so all these coefficients will be given by this factor, and then you have these p's powers of p's and q's. Okay. So, if we use now instead of carrying on with n1 and n2 for these steps to the right and to the left, we can alternatively carry with capital N and M. So, use them instead, and that can be easily done because your n1 equal to half of capital N plus small m, and N2 is equal to half of capital N minus small m. So, we have replaced this quantity as you see here, P n N1 N2, we have now replaced it by P n m, and this can be written as P n m is equal to n factorial divided by half of n plus m factorial half of n minus m factorial, sorry, let me close the bracket, and then of course, we have p to the power n plus m by 2 and q to the power n minus m by 2. Okay. As I said, capital N is positive definite number, some number which is large, and m could be either positive or negative. Okay. So, now we ask the question, what is average of m? So, what is the average number of steps taken towards right by the man? That is what is N1 average. Okay. Now, this is the probability distribution that you see here. Okay. So, this is the probability distribution, or this is the probability, and we want to calculate the average number. Now, you understand that if you have are doing a few subjects, each one has some weightage, which means that the credits are called weightage. Suppose you are doing 3 subjects, say for example A, B and C, they could be statistical physics, mathematical physics and quantum mechanics, and this has a weight say 4, this has a weight say 6 and this has a weight say 2. So, the average grade will be whatever the grade you get. Suppose you get a grade. So, let me change this nomenclature from A, B, C to P, Q, R. Okay. And so, these are the 3 subjects, statistical physics, mathematical physics and quantum mechanics. So, in P you get a grade A, which means it is equal to 10, and in subject Q you get a B grade, which means it is equal to 8, and in subject R you get a grade say again equal to say B, which is equal to 8. So, your average grade or the grade for that particular semester is going to be 10 into 4, because you got a 10 in a 4 credit course, and 8 into 6 plus 2 into 8 divided by all these total credits, which are 4 plus 6 plus 2, which is 12. So, this will give you your average grade, and so this is equal to 40 plus 48, that is 88 plus 16, which is equal to 104 by 12, and whatever it comes, that is going to be your average grade. So, we are asking this question, what is the average number of steps taken towards right, which we know is there he has taken n1 steps towards right. So, the average of n1 is n1 bar, and the probability distribution, which is analogous to the credit of the course, is given by this boxed expression, which is P of n m. Okay. And we have to calculate n1 using this distribution, and n1 is just what we have discussed, is equal to n1 P n of, we can write it as m, but we can also write it as n1 here, because n1 and m are related, they are related to n and m and so on and so forth. So, this is equal to, and this is n1 equal to 0 to n, all possible values of n1, and which goes from 0 to n, and this is equal to n1 equal to 0 to n factorial divided by n1 factorial n minus n1 factorial. N1 p to the power n 1 and q to the power n minus n 1, because n 2 is nothing but capital N minus n 1. Remember that n 1 plus n 2 is equal to n. So, that is the average number of steps taken towards the right, and if you notice it that there is a p del del p, this p is the probability to the right. So, this p to the power n 1 is equal to n 1 p to the power n 1. So, this is what you want here, which means you can take a derivative with respect to p for this in order to get this n 1 bar or the average value of n 1. Okay. So, n 1 bar comes out as, so we replace this thing here, okay, and which can be written as, because nothing else depends on p, it is a del del p of sum over n 1 equal to 0 to n capital N factorial divided by n 1 factorial n minus n 1 factorial and p to the power n 1 q to the power n minus n 1. And this is nothing but the binomial distribution. You see it here. This is the binomial distribution that you see at the bottom of the page. So, we can simply write it as the bottom of the, the binomial distribution. So, this is like p del del p of p plus q whole to the power n, and this is nothing but p to the power n p plus q to the power n minus 1, and we know that p plus q is equal to 1. That is because the total probability, either he has to take a left or he has to take a right, or right plus left should be. So, he has to take a step. It is not that he does not take a step at any given instant of time. So, he takes either a left step or a right step. So, the probabilities will have to add up to 1. So, that gives that n 1 average is equal to p n. So, this is a nice and important result, that average number of steps he takes towards the right is the probability multiplied by the total number of steps. Okay. And similarly, we can do the calculation for n 2, and n 2 bar, that is the average value of steps taken towards left, would again come out as q into n. Okay. And then n 1 plus n 2, which you can write it, say for example, because your n equal to n 1 plus n 2. So, the average values of this is going to give you n 1 plus n 2 average equal to n 1 average plus n 2 average. Okay. So, this average of the sum is sum of the averages, and this is equal to n into capital N into p plus q, which is equal to 1. So, this is equal to n, which it should be. Okay. So, sum of the averages is equal to 1. So, now what is the average value of m? That is, what is the average value of the difference in n 1 and m 2, that is whether he has taken more steps to the left than to the right, or vice versa and so on, and this m is equal to nothing but n 1 bar minus n 2 bar. So, the difference between the averages is same as the average and these two subtracted from each other. Okay. So, what I mean to say is that if you have this, and it can be written as this, this is nothing but n 1 average minus n 2 average. So, what holds for addition also holds for subtraction, and this is equal to n into p minus q, and so this is the this m average. So, the average number of steps which is a difference in the average between n 1 and n 2 is given by n into p minus q. So, in a special case, if p equal to q equal to 1, rather half, that is if we there is equal probability to take left step and right step, then as understood that this difference should go to 0. Okay. But in general, of course, that is not true, that we know, and there is one more important quantity called as the variance or the dispersion of m, which means that this you have delta n, we get it through this delta n 1 square average, which is nothing but equal to n 1 minus n 1 average square and a bar of it, and this is equal to n 1 square average minus n 1 average square. Okay. And this is your variance of n 1, and of course, we will get similarly we can get m or n 2. So, variance of say for example, n 1 or n 2 or even m can be calculated in a similar fashion. Okay. And how do we get this? We already know this. We have to calculate this. Okay. And the way we do it is simple. Again, we have to have this n 1 square average, which is equal to sum over n 1 from 0 to n 1 square p n of n 1. Okay. And this is same as n 1 equal to 0 to n 1 square, and you have a n, well, let me write this as earlier. First, let me write the factors n 1 factorial, n minus n 1 factorial, and n 1 square, p to the power n 1 and q to the power n minus n 1. Now, once again you see that n 1 square p to the power n 1, okay, it is equal to p del p of square p to the power n 1. Okay. So, we will replace it here, and replacing it we get n 1 square average is equal to p del p square sum over n 1 equal to 0 to n factorial divided by n 1 factorial n minus n 1 factorial p to the power and q to the power n minus n 1. Okay. So, this is the simplified form, and this is nothing but, then again this is nothing but the binomial distribution. And hence, this is equal to p into del p square of p plus q whole to the power n, and this is nothing but n 1, if you do the simplification, it is n 1 bar square plus n p q. Okay. So, this gives that delta n 1 square average is equal to n 1 square minus n 1 average square. This is equal to simply n p q. Okay. And as a special case, if p equal to q equal to half, then of course, it is equal to n over 4. So, this is called as dispersion, or it is called as fluctuation. Either it is called as a dispersion or variance, as I said. dispersion, fluctuation or variance in n, n1 that is. Okay. So, now if you take the relative fluctuation, that is you calculate that this is called as the delta n RMS, we take the root of that. So, delta n RMS divided by n1 average, this becomes equal to 1 by, so this is root over of delta n1 square average divided by n1 average, and this goes as 1 by root over n. So, this is an important quantity that we will see that the relative fluctuation in the calculation of various thermodynamic quantities, they actually go as 1 by root over n, and as n goes to infinity, this fluctuation drops out or becomes 0, which is when the result becomes the fluctuation, when it goes to 0, the results become accurate, and that is why we need large n, and this is also encoded in thermodynamics, what we say as the thermodynamic limit, which is defined as n going to infinity, v going to infinity, but the density of particles remaining a constant, which means n by v is a constant. Okay. So, this is very important, and we need this throughout statistical mechanics, and we can find out variance of n2. We can do that. So, this can be done, and once when we do that, your m becomes equal to n1 minus n2, or you do not need actually the variance of n2 to get a variance of n, because this is nothing but 2 n1 minus n, and a delta m, which is m minus m average, this is equal to 2 n1 minus n and minus 2 n1 bar minus, that is average, minus n, and this is nothing but 2 n1 minus n1 average, which is equal to 2 delta n1. So, delta m is nothing but delta n1, and that is why we have this delta m square is equal to 4 times delta n1 square, and so on, and then this is nothing but it is equal to 4 times delta n1 square is 4 times n into p into q, and once again if p equal to q equal to half, of course m average does not make sense, but this gives you that delta m square average, this still exists, which is equal to 4 n p q, and for p q equal to half, this delta m square average is equal to 4, I mean it's p in p equal to half, q equal to half. So, this cancels and we get n. Of course, the random walk problem is nice, it teaches us this statistical analysis, how to deal with large systems and with certain probabilities something is happening, with some other probabilities that something is happening. However, I mean this problem can be made more complicated. We have taken a one dimensional sort of random walk that we which means that this right and left, we still continued with that, but in a 1D there is no right and left, but you can talk about okay. So, you can still talk about a right and left. So, there is a right step here and there is a left step here and so on. So, in this 1D random walk, then we have these results, important results coming by, and we get these variances or the fluctuations which do not vanish either for the n1, n2 or for m, whereas for if there is an equal probability for P and Q, that is taking a right step and a left step, then the difference in the steps, that is m average, would go to 0, but nevertheless delta m square average is not equal to 0. We can introduce complexity into the problem by considering a 2-dimensional random walk, in which there will be more probabilities, that is going towards east, west, north, south and so on, or we could even make it more complicated by assuming that the step size does not remain same. But these are more difficult problems, and let us just stick to things which are simpler and easier to understand. So, let us do this, the next problem let us do as the coin tossing problem. Okay. And you will see that the outcomes of these two problems are same. So, consider flipping a coin n times, and you record the difference between head and tail. H minus T, where H is the number of heads and T is the number of tails. Okay. So, record this H and T, and because there is equal probability of having a head and a tail, which corresponds to P equal to Q equal to half in the earlier problem, this quantity, if you call it as M, the average of M is always equal to 0. So, there is no point in talking about average of M, rather what we will talk about is this M square average. Okay. So, each flip contributes Ni equal to plus minus 1. Okay. So, you ask this question, what would be M n, which is sum over I equal to 1 to n Ni, which is equal to H minus T. Okay. So, this is the question that we ask, and as I said, M n average is equal to 0, because there is equal probability of having head and tail. So, this is not useful, but what could be useful is the RMS value. Mn, which is nothing but it is given by Mn square, and then we take this average and then take the square. So, let us do it by induction. Let us do after one coin flip what happens. And what we have is this is equal to half into minus 1 square. So, this is for this M1 square. Okay, so, this is equal to plus half into plus 1 square, and this is equal to 1. So, after 2 coin flips, 2 coins flip, you ask this question, what is M2 square average, and this is nothing but 1/4. So, this is tail and this is head. So, for 2 coins it will be minus 2 square plus half into 0 square plus 1/4 into 2 square. Okay. So, this is tail. Tail is corresponds to minus 1 and head is plus 1. So, this is head tail or tail head, and this is the head. Okay. So, then you have after 3 coins flip, m3 square is equal to it's a 1/8 of this 1/8 of minus 3 square plus 3/8 of minus 1 square plus 3/8 of plus 1 square plus 1/8 of plus 3 square. This is tail 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 for 3 flips. This is 2 tail and 1 head. This is 2 head and 1 tail, and this is head head head. Okay. So, and this is nothing but equal to, so this is equal to 2 and this is equal to 3. So, you see that m1 bar square is equal to 1, m2 bar square equal to 2 and m3 square bar equal to 3, which means that whether we have mn square bar is equal to n. We have shown it for 1, 2, 3 does not mean that it will carry over for n when n is, especially when n is large. Okay. So, we want to check whether this is true, and this can be seen that this mn square average is nothing but the RMS value after n minus 1th step, after n minus 1 steps plus the last step, that is the nth step. Okay. And let us see how what this comes. So, it is mn square bar equal to mn minus 1 plus nn, this nn is the last measurement that we do, and the square of that, and then taking the average, and this is equal to m n minus 1 square average plus a twice of m n minus 1 into n n, and that average. See that this we are using bar, but in some text you can use an angular bracket, and that can also be used, plus n n square average. Okay. So, if you look at the middle term, that is this term, which is the product term, which is m n minus 1 n n average, this will be nothing but half m n minus 1 into minus 1 and plus half m n minus 1 into plus 1. Okay. So, because your n is equal to, you are taking the average, your n n, that is the last coin tossing, would give you a plus 1 and a minus 1 with average with this factors weights as half and half. Okay. And this is equal to 0. So, which means that we are left with only this term and this term goes to 0, and that will make things a little easier for us, and that will tell us that m n square average is equal to m n minus 1 square average plus 1. Now, this is equal to n minus 1 by induction, and if this is true, then m n minus 1 square average is equal to n minus 1 plus 1 equal to n. Okay. So, this is indeed what we were thinking, that m n square average equal to n. So, the RMS value, RMS means we have used this earlier, I have not elaborated, it is a root mean square. So, you first take a square and then you take a mean and then you take a square root. Okay. So, this is equal to square root of m n square average, and this is nothing but the RMS of h minus t, okay, and this is equal to root over of n. Okay. And again if you take the relative dispersion, then it will go as 1 by root n. Okay. So, we ask this question that in both these cases what is the trajectory like if you take n steps and have gone a distance root over n, and that was the question that we were trying to answer. And I think it is clear now that these two problems that we have done, that is the random walk problem and the coin tossing problem, they have a formal similarity, and the similarity says that the relative fluctuation or the relative dispersion of the measurements that go as 1 by root over n. And if it is 1 by root over n for n going to be large, these fluctuations will disappear or will vanish or tend to vanish, and we would get the results from statistical mechanics to be accurate. So, as n becomes larger and larger, the values of the thermodynamic variables or values of these measurements of say mn or mn square or these n1 average or n2 average etcetera that we have talked about for the earlier problem, they start becoming more and more accurate, and this is the power of statistical mechanics, and we are going to see it for these thermodynamic systems through the concept of ensembles and so on.